In this lesson, we are going to look at the physical pendulum. So it's a departure from our simple pendulum analysis that we had been using. Remember, the simple pendulum was simply a point particle. We had a massless string connecting it to the top, and then it would oscillate back and forth. Now we are using a more physical system, and I drew it as like a blobby bowling pin type object we have here, but it really wouldn't matter. It applies for any shaped object, but we have our bowling pin shaped object, and I literally peg it, pin it at the top. So our pivot point is up here. It would oscillate back and forth as shown, right? And that's our physical pendulum. Well, to get the equations for this type of oscillation, we're going to start out with torque equals I alpha, because remember, now we have not a point particle system. We cannot use mr squareds. We have to use the parallel axis theorem. So as I have here, please make sure you get this into your notes, that if we were given actual numbers, that I would be calculated using the parallel axis theorem. And normally, when you have R cross F with mg, right, here is our R cross F, and the force is mg, we would not get 90 degrees, but we know the restoring component of mg is only due to the tangential component, so just due to our mg sine theta. So when we draw the r and the mg sine theta from a common origin, there we have our 90 degrees, and that's the 90 degrees that I have indicated here. So the sine theta here comes from the tangential component, not from the sine theta in the cross product. And we're even going to lose that sine theta because we are again going to look at our small angle approximation, right? So when this angle theta is 10 degrees or less, sine theta to a very good approximation becomes theta. And we have our calculus version of torque equals I alpha. So alpha is the second derivative of the position function. So we have our differential equation in place. It is of the form, exactly of the form mathematically that we had with the block oscillator. So we're going to assume the same mathematical form for the solution, a cosine omega t. We are going to substitute in theta here for theta here. So we get negative mgh, a cosine omega t, and I'm going to put the a in here. It looks like I dropped an a somewhere, so please make sure you get the a in there. When we take the second derivative, we need to take the first derivative and then take the derivative of that. So our cosine derivative becomes a sine and then negative sine, so that's where the negative comes from. Then the derivative of sine is positive cosine, so we get our cosine back, but again, the derivative of the argument gives us another omega, so it works out identically to how it worked out with the block oscillator and the simple pendulum. Get a lot of nice cancellation. We lose the a, we lose the a, we lose the cosine omega t, and we have our expression for omega. So omega equals the square root of mgh. We have our equivalent variables here as well. And for all of the harmonic oscillators, whether it's the block oscillator, the simple pendulum, the physical pendulum, or in our next page of notes, we're going to have a torsion pendulum, the omega that you want to memorize is always the block oscillator basic form, omega equals root k on m, and then focus on the equivalent variables. So look at the problem and say, well, what would correspond to mass? Mass is an inertia term, so for the physical pendulum, mass and inertia go one-on-one together. Remember, for the simple pendulum, we noted that the k went directly with the g. So k and g go together, but for the physical pendulum, you have to kind of just memorize that that gets transformed into an MGH. Or if you have the ability to look up what the equivalent variables are. So, understanding the block oscillator and the basic structure of that mathematical solution, you can see, is critical to understanding the other systems that we're looking at. So I'm again going to zoom out here so you can pause here and make sure that you get down all of the annotations you need for the physical pendulum.